Yes. So in quantum numbers, we have four quantum numbers. The first one is principal quantum number, which is indicated by n. Principal quantum number n. So what does it indicate, sir? Principal quantum number was used in identifying the size of orbital. Initially, the size variation. How big a particular orbital is indicated by principal quantum number. And who proposed that? Niels Bohr's concept was retained there. So Niels Bohr proposed principal quantum number, and main idea of Niels Bohr is retained for single electron system. For any single electron system, the concept of Bohr's atomic model is true. It is valid. But for multi-electron system, it failed. Okay. So proposed by Niels Bohr. And what is this principal quantum number? It mainly signifies, it signifies the size or energy of different orbitals. Energy of different orbitals. What are the limitations of this n value? N can have values 1, 2, 3, 4, and so on up to n, of course, all integral values. And it indicates the main energy level. It indicates the main energy level to which an electron belongs. The main energy level to which an electron belongs is indicated by principal quantum number. That means, so first energy level, second energy level, third energy level. So that way, the number, principal quantum number will give us the idea of main energy level. Of course, sub energy level is subshell or main shell, main energy level or shell here. Okay. So what additional information do we get with this principal quantum number? Along with this, each energy level or each shell has different names, as you know. Each shell has different names. N equal to 1 corresponds to K shell, N equal to 2 for L shell, N equal to 3 for M shell, N equal to 4 for N shell, and so on. It continues. Okay, those points are very clear. Small points, and you all know them. There is nothing much. You have been studying that from 10th class. Okay, so what additional information do we get from this principal quantum number? Angular momentum. You know this formula also. Angular momentum of electron in a shell. Momentum of an electron in a shell or in an orbit is given by mvr is equal to nh by 2 pi. And how do we write it? Nh cap also. Nh by 2 pi or nh cap, the other formula. Next, so what else does this principal quantum number indicates? N value is equal to, n value for a particular energy level is equal to number of subshells in it, isn't it? number of subshells. That means if n is equal to 1, for n is equal to 1, only one subshell is present, S subshell. For n is equal to 2, S and P subshells are present. If n is equal to 3, S, P, D, 3 subshells are present. Like this, the n value indicates number of subshells. It also indicates number of orbitals. Number of orbitals in given energy, given shell containing a particular principal quantum number n is given by number of orbitals. What is the formula? Number of orbitals is equal to n square. Just remember them as short formula. Number of orbitals is equal to n square. So what is that n square? Here, for example, if n is equal to 1, the number of orbitals is equal to 1 only. Only 1s orbital is present in it. Number of orbitals is 1. If n is equal to 2, number of orbitals will be equal to 4, isn't it? 4. How they are? 4s are 1s orbital and 3p orbitals. Here only 1s orbital. 4 here is because of 1s orbital and 3p orbitals, together 4. For n is equal to 3, the number will be 9. For n equal to 4, n is equal to 4,
16.
16. Like this, the number continues. Number of orbitals, remember that. And we can also get number of electrons present in a given main energy level. If n square is number of orbitals, number of electrons will be 2n square. Because each orbital takes 2 electrons.
2 electrons.
Okay. Number of electrons is equal to, just add that formula. Number of electrons is equal to 2n square. Okay. See next, one more point we can add to this principal quantum number. N value indicates the n value gives the energy of a energy based on n value, energy of a particular orbit or particular shell or particular main energy level can be identified. Energy order can be given for only single electron system. The main point here is for any single electron system, the energy of orbital depends only on n value orbit. For an orbital also, of course, like you can take 2s, 3p, 4d, something like that. For any orbital, the energy depends only on n value if it is a single electron particle. Remember that. I'll also repeat that later. So the main point here is for a single electron particle, energy of orbital depends only on n value. Only on n value. If n value is same, energy will be same. For example, 1s orbital is taken. 1s orbital. It has some lower energy. You know that. If 2s is taken, n value is 2 here. N value is 1 here. N value is 2. For 2s, energy will be more than 1s. And if 2p is taken, for 2p, is it less than or equal?
Less than.
Look at the point written above.
Okay, yeah, equal.
If n value is same, energy will be same for any single electron particle. Remember that. Example for hydrogen. You take for hydrogen atom. Or He plus ion. Any single electron particle can be taken. Heavy ion or molecule atom. If energy order is required, it depends only on n value. That is the point here. 3s, 3p, 3d, all of them have same energy. Less than 4, all, and then it continues. The Moeller diagram order actually is for multi-electron system, not for single electron system. You may get a question, sir, why is this order? This is not practically correct order for all electron, for all elements. They are all multi-electron system. For hydrogen, we will write configuration only up to 1s. But for helium, this order is not followed because it's multi-electron particle. Their Moeller diagram order comes, and there the value depends on n plus L value. Energy depends on n plus L value. We'll see that. Okay. So these are the details of principal quantum number. Next, azimuthal quantum number. Azimuthal quantum number. Azimuthal quantum number, it's written as L, and K is actually initially proposed azimuthal quantum number, which was later modified into L. We'll see that. Azimuthal quantum number. Okay, and what are the other names for it? Also called as subsidiary quantum number and angular momentum quantum number, because its orbital angular momentum is given by it. Angular momentum quantum number. Angular momentum quantum number. And who proposed it? Sommerfeld or Sommerfeld. And what is its main point, main significance? L signifies what? Any guess? L signifies
Shape of the orbital.
shape of orbital. Shape of orbital. How, sir? If L, or let me first write the values of L and then we'll write the shapes. Value of L, L value depends on N value, isn't it? Depends on N value of given shell. That means if N is equal to 1, L value, or let me first write the general L value. L is equal to given shell. Okay. L value is equal to 0, 1, 2, and so on up to N minus 1. This is how L value depends on N. That means if N is equal to 1, possible L value is only 0. Maximum value is N minus 1. So L value 0, and L value 0, it corresponds to S subshell. S subshell or S subshell, so which has spherically symmetric structure. Spherical. If N is equal to 2, L values possible are L equal to 0 and L equal to 1. L equal to 0, this is again S subshell. This is P subshell. And for p subshell or p orbital, the shape is dumbbell, as you know, dumbbell. And then for n is equal to 3, possibilities are L value 0, 1 and 2. That means S, P and D subshells are possible. For D subshell, the shape, you know, double dumbbell. For L value, for L value 2D, what about the other values possible? L is equal to 3, L is equal to 4, L is equal to 5. For L3, F, G, H. S sub S, P, D, S, P, D, F, they came from spectral terms. These symbols, these letters came from spectral terms: sharp, principal, diffused, fundamental, like that. S for sharp, P for principal, D for diffused, and F for fundamental. So these are the meaning of those terms. What about G and H, sir? They are continued. They are continued after F in alphabetical order. They don't have any particular abbreviated forms. Okay. So next. So particularly L signifies shape of orbital. And then what other information can we get from L values? If number of orbitals corresponding to a given in a subshell can be calculated. What is the formula for it? 2L plus 1. Number of orbitals. That means for S, L is 0. So orbitals number is 2 into 0 plus 1. Isn't it? 2 into 0 plus 1. How much? 1. So there is only one s orbital possible. For P, L is 1. Substitute L value 1 in this formula. 2 into 1 plus 1. Okay. The orbitals number will be 3. And D,
5.
5. F,
7.
7. G,
9.
H,
11.
how much? 11.
11.
So they continue like this. So these are orbitals number. If orbitals number is known, you can also find number of electrons, maximum number of electrons that can be accommodated in a subshell. Maximum number of electrons that can be accommodated in a subshell will be equal to 2 into 2L plus 1. So if orbital number is 2L plus 1, number of electrons will be 2 into 2L plus 1. Okay. Next, another important point here is orbital angular momentum. The name itself says orbital momentum, angular momentum quantum number. Orbital angular momentum is calculated by using a particular formula. Orbital angular momentum is equal to root over L into L plus 1 h by 2 pi, or root over L into L plus 1 h cap, root over L into L plus 1 h cap. So what is this orbital angular momentum? Orbital angular momentum is calculated by nh by 2 pi. For a given orbit, it is nh by 2 pi. But for an electron in a given orbital, the angular momentum is equal to root over L into L plus 1 h by 2 pi. Know the difference. That means orbital angular momentum for s orbital will be orbital angular momentum for s orbital will be equal to how much? Look at that. L value for s orbital is 0. Then this value will be equal to 0 into 0 plus 1 into h by 2 pi. What is that value? 0.
H by 2. Yeah.
Root over 0 into 0 plus 1.
0.
0 into something is 0. Root 0 is also 0. So the orbital angular momentum for s orbital is 0. That is actually given. That is actually observed. To get 0 orbital angular momentum, the possible value of L should be 0. But Sommerfeld initially proposed that K value is the orbital angular momentum quantum number or azimuthal quantum number. According to the initial Sommerfeld azimuthal quantum number, K values, the values are from 1 to n. Sommerfeld's azimuthal quantum number, K value, they have values from 1 to n. There is no 0 value. If there is no 0 value, you will not get any 0 orbital angular momentum for S subshell. So that's why the value is modified. K value is modified into L, so that L values are from, all the L values are equal to K minus 1 values. Possible L values are K minus 1 value. So if K value is 1, L value should be 0. If K value is 2, L value should be 1. Like that, highest value of L value is n minus 1 not equal to n. So that way, just to get this orbital angular momentum value 0 for S subshell, the values of K, value of K is modified into L. K has no 0, but L value should have 0 to indicate orbital angular momentum of S subshell. Right? Okay. So these are the main points of azimuthal quantum number. The importance of azimuthal quantum number in a particular given shell, in a given shell, the number of different subshells or types of subshells present in it can be given by using the values of L. And also orbitals number or electrons number can be calculated by using this particular formula. Okay, you just remember this formula. This is very important. Orbital, angular momentum of an electron in 3s orbital is, 4p orbital is. That way the questions will be given. So if they ask for angular momentum of an electron in a given orbital, whatever it is, orbital, then use its L value and calculate the value. Finally, you will get orbital angular momentum. Okay.
Yes.
Orbital example for a subshell, orbital angular momentum is equal to how much? 0. For p subshell, how much it will be? Root over, for p subshell, L value is 1. Root over 1 into 1. 1 into 1 plus 1, root 2. Isn't it? Root over L into L plus 1. 1 into 1 plus 1, root 2 h by 2 pi. For d subshell, 2 into 2 plus 1, root 6.
Root 6 by
H by 2 pi, like this. Okay, so this is the information that can be obtained from azimuthal quantum number. And the third quantum number is magnetic quantum number. Magnetic quantum number. M or ML. Both the symbols can be used. M or ML is its notation. For spin quantum number, we also use MS along with S. Who proposed this? Lande is the scientist who proposed magnetic quantum number M. Okay. So what is its, what does it indicate? Signifies? It signifies orientation, isn't it? Orientation or direction of a particular orbital of a given orbital. What it means? For example, S subshell is taken, it is spherically symmetrical. Px subshell is oriented along x-axis. Py orbital is oriented along y-axis. Pz orbital is oriented along z-axis. So that information is provided by magnetic quantum number. It is also called as directional quantum number. Its other name is directional quantum number. But very less used term. Next, signifies orientation of given orbital. Then what are the value? Value of m, value of m depends on L values. L value. M can have values from minus L plus 1, and so on 0, comma 1, and so on up to plus L. The possible values of M, magnetic quantum number, is this range minus L to plus L including 0. That means if L is 0, what are the possible values of M? M can have only 0. Minus 0, 0 plus 0. Whatever it is 0. Only 0. What does it indicate? S subshell. For L is equal to 1, possible values are M can be minus 1, 0, or plus 1. Okay. So what does it indicate? Sir, 0 conventionally indicate PZ orbital. 0 M value conventionally indicate PZ. Even M value 0 for D subshell also indicate dz square. So how, sir? How it is actually? This is the quantum number which indicates the direction of angular momentum. The direction of angular momentum. And there is a mathematical relation also. It depends on the cos theta, angle of orientation, like this. The orientation, if this is the magnetic field, you know, magnetic quantum number was proposed to explain the splitting of spectral lines in presence of magnetic field. Nothing but Zeeman effect. Magnetic quantum number was proposed to explain Zeeman effect, or it could successfully explain Zeeman effect, the splitting of spectral lines in presence of magnetic field. So what happens are, in presence of when the sample is taken, sample whose spectrum is collected is placed under external magnetic field. The lines appears will be combination of very sharp lines. The spectral lines that are formed on the screen are combination of very finite, very small lines. So that is observed, of course. The reason for that is when external magnetic field is placed near the sample, all these orbitals, they change their orientation in some particular directions. A subshell has no particular direction, leave it. So all the 3 p subshell, p orbitals are there. All the 3 p orbitals are in same direction in the absence of magnetic field. Whenever the sample is placed under the magnetic field, the p subshell, p orbitals will orient in particular directions. The orientation difference, the direction difference comes only when magnetic field is placed. So when that direction change, orbital angular momentum quantity will also change. Orbital angular momentum, it's a vector quantity. Vector quantity will also depend on the direction. So if magnetic field, external magnetic field is on this direction, magnetic field is on this direction, dz orbital orientation will be on this direction. And here angle is 90 degrees. And this M value is proportional to cos theta. M value is proportional to cos theta. If cos 90, what is cos 90? 0. Something into cos 90 it is. Cos 90 is 0. Only for dz orbital, the angle is 90. So that's why I don't want to explain all the details to you. There is a mathematical relation to explain this. So according to which, for Pz subshell, conventionally m value is taken as 0. And similarly dz square, for dz square subshell, m value is taken 0. Sir, what about -1 plus, sir? You can allot -1 plus 1 to any of the other two p orbitals. That means you can take px or py with m equal to -1, py or px, py or px with m is equal to +1. Is that clear?
But sir, in the first case, M is also 0 now. We've taken S.
This is for S subshell. In S subshell, only one orbital is there. So that orbital gets m value 0. In P subshell, let me write in box configuration. In P subshell, there are 3 orbitals.
Yes.
There are 3 p orbitals. One gets -1, one gets 0, other gets +1. In
Got
S
it.
subshell, there is no choice, always 0. In P subshell, 3 p orbitals will get 3 different values. One gets 0, one gets -1, other gets +1. For L is equal to 2, possible m values are -2, -1, 0, +1, +2. Here also 0 is conventionally given for dz square, and all the others can be given for any other orbitals. What are the different d orbitals we have? dxy, dyz, dxz, dx square minus y square, and dz square. These are the 5 d orbitals. So the 5 values of m value, m corresponds to 5 d orbitals. Especially magnetic quantum number has no significance, but the number of magnetic quantum number values has significance. Number of m values have significance. Whether m value is only 1, m value is only 3, or m value is 5, or m value is 7. So that gives us the information of number of orbitals present in a given subshell. Different orbitals indicate different orientation. So finally, magnetic quantum number indicates the direction of orientation of particular orbital. So any other information that can be obtained here? Not much. See the next one. These first 3 quantum numbers are derived from Schrodinger's wave equation, and the fourth one is spin quantum number. Spin quantum number S or small s, actually S or ms. S or ms. So proposed by Goudsmit and Uhlenbeck. Proposed a particular quantum number, and this was proposed actually to explain the Stark effect, the splitting of spectral lines in terms of electric field. The Stark effect was observed when the sample of atoms is placed in presence of external electric field. There is a splitting in, further splitting of spectral lines. And to explain this particular thing, the people assumed that there is another angular momentum along with orbital angular momentum, which is the reason for the splitting of spectral lines. If angular momentum changes, the value or direction changes, the splitting of spectral lines can occur. It's a highly complicated concept. For basic knowledge, you can understand like this. If orbital angular momentum value or the direction changes, the particular energy difference will occur and the splitting of spectral lines can occur. Different spectral lines can be possible. It means that. And even after observing this magnetic field concept, electric field concept was explained by using the spin of an electron. So what is that spin of electrons or spin angular momentum? Especially spin means here spin angular momentum. So how does this spin angular momentum arise? Electron revolves around its own axis along with its revolution around nucleus. Electron has revolution along its own axis like this, either in clockwise direction or anti-clockwise direction. For example, electron revolves in two directions like this. Consider its own axis. Electron is revolving. So this is electron. This is electrons. It's spinning like this, either in clockwise direction or in anti-clockwise direction, like this. Because of revolution of electron, a charged particle along its own axis, spin angular momentum generates. Spin angular momentum arises. So spin which is also called simply spin. Actually, what we consider in basic level, what we learn is spin means revolution of electron around its own axis. In simple terms, you can understand that, but in original terms, it is not that. Spin is not clockwise rotation or anti-clockwise rotation. Spin is the angular momentum that arises due to revolution of electron in clockwise or anti-clockwise direction. It's an angular momentum term. Am I clear? Spin is a term related to spin angular momentum. Okay. So corresponding to different spins, different quantum numbers are assigned, different S values are assigned. While assigning the S values, the main condition that was considered is for all the other three quantum numbers, the difference between any two successive quantum numbers is only one. Can you observe that? The difference between two successive quantum numbers is one. For example, principal quantum numbers are taken 1, 2, 3, 4. The difference is 1, 1. Next one, azimuthal quantum number values 0, 1, 2, and so on up to n minus 1. There also the difference between two successive values is 1. Even in this magnetic quantum number also the difference is 1. 0, minus 1, or minus 1, 0, or 0, 1, 1 and 2, like this. Similar to those three quantum numbers, they tried to give two spin quantum numbers, or two which indicate clockwise and anti-clockwise spins, whose difference is also equal to 1. They want two values. One should be positive, one should be negative. Positive spin indicates clockwise revolution of electron, and negative spin should indicate anti-clockwise revolution. So there should be two values. One should be positive, other should be negative, but the difference between them should also be 1. For that combination, the values they obtained is this plus half and minus half. Plus half and minus half are obtained in such a way the difference is 1. Is there any other possible combination? One should be positive, other should be negative. The difference between them should be 1. Of course, they should be same also in magnitude. You can't take plus 1 by 4 minus 1 by 4, or plus 3 by 4 1 minus 1 by 4, or you can't take plus 1 and minus 1. The difference rule will not be valid. They should be same in magnitude, opposite in spin, and the values difference should be equal to 1. So in such a way, the values of spin quantum numbers are selected as plus half and minus half. Okay, sir. What actually it indicates? Of course, ultimately, these values indicate clockwise or anti-clockwise spin of electron. Clockwise or anti-clockwise spin of electron. Actually, spin means here spin angular momentum of electron, which arises due to revolution along its own axis. Okay. So what other information do we get with this spin quantum number? Spin angular momentum. As I said, spin angular momentum is equal to root over s into s plus 1, s into s plus 1 h by 2 pi. Spin angular momentum is equal to s into s plus 1 h by 2 pi, where s is only magnitude. Only magnitude should be taken. No need to take sign. S is always equal to 1 by 2. Don't take plus or minus. It's just 1 by 2. Only magnitude. Then what is that value? 1 by 2 into 1 plus 1 by 2. 3 by 2. That means it's root 3 by 4. 1 by 2 into 1 plus 1 by 2. Root 3 by 4 h by 2 pi. Or root 3 by 2 h by 2 pi. This is a fixed value. Spin angular momentum is fixed value. It's not like orbital angular momentum. L value changes, so orbital angular momentum value will also change, but spin angular momentum will be same for a given electron. It is for a given electron. Okay. Is there any confusion in it, Janvi?
No, sir.
Completed writing?
Yes, sir.
Okay, so this is the information about the 4 quantum numbers. With the help of these 4 quantum numbers, we can give the details of a particular electron in a particular atom. Details of electron in a given atom. So electron is present in which main energy level? It is present in which sub-energy level? It is present in which orbital? It is present in, it has which particular spin? All the details can be given with the help of these 4 quantum numbers. Then orbital is designated as, orbital notation is given like this. Orbital notation is in the form of NLX. NLX. What it is, N is principal quantum number. You know this, principal quantum number. Number should be given. L indicates here type of orbital or subshell. Type of orbital, not the value, it's type of orbital, S or P or D. That should be indicated. Here X is number of electrons in it. NLX notation. For example, so what are the possible orbitals? For n is equal to 1, what is the possible orbital? 1s. For n is equal to 2, possibilities 2s and 2p. For n is equal to 3, the possible orbitals are 3s, 3p, 3d, and so on. They continue. Now, energy order. Here, that point we missed in case of Ashbetal quantum number. Okay, we'll write that here. Energy order of different orbitals. First condition for single electron particles. For single electron particles. For single electron particles, energy is directly proportional to only n value. Energy is proportional to n value. If n value is same, energy will be same. I told you already just now. That means 1s has particular value less than 2s, which is equal to 2p. Okay, then 3s, 3p, 3d, 4s, 4p, 4d, 4f. Like this. If n value is same, energy will be same. All the electrons present in the given main energy level will have same energy for single electron particles. That means 1s is taken as first energy level, or it is taken as ground state. Okay, it is all related, it is all similar to that of Bohr's model. Two S and 2p is called as second energy level. First excited state. First excited state. 3s, 3p and 3d together is called as third energy level. It's not excited level, energy level, right? Clear. Energy level. And what it is called as second excited state. Second excited state. Here we have a term degeneracy of a particular particular energy level. Degeneracy. Let me first tell you what it is. Degenerate orbitals, you must know. What is degenerate orbital? Orbital having same energy, isn't it? Degenerate orbitals are the orbitals which have same energy. Degeneracy means its number of degenerate orbitals. Number of degenerate orbitals is called as degeneracy. Number of degenerate orbitals means, or number of orbitals having same energy. Having same energy. Okay. What it means, sir? For this single electron system, calculate that degeneracy. Ground state degeneracy is, how many orbitals are there? Only one orbital. So degeneracy is 1. So for ground state, degeneracy is equal to 1. For first excited state, how many orbitals are there in this? 2s and 2p together?
2.
Orbitals. 2p is one subshell. How many orbitals are there in it? Yes. For, let me just give you in the form of a short formula. For single electron particles, degeneracy is equal to n square. Degeneracy is calculated directly with n square formula. For first ground state means n is equal to 1. So degeneracy 1. Excited state is n equal to 2 state. 2s and 2p. 2 square. That means 4. How 4s are? 1 is 1 s orbital. P orbitals are 3. Like this. For second excited state, For second excited state, what is the degeneracy? It is 9. How 9? 1s orbital. Look at
3p
this.
orbitals.
3p orbitals and d
5d.
5d orbitals. Like this. So this is all about single electron particles. What are the single electron particles? Like hydrogen, He plus, Li2 plus, okay, Be3 plus, etc. Completed. Then see for multi-electron particles. Multi-electron particles. That means ions or elements. Energy depends on n plus L value. This is Aufbau rule. Based on Aufbau rule or general order also. N plus L value. If n plus L value is same, n plus L value is same, then energy is directly proportional to n value. N value. That means first energy level is 1s. First energy level or ground state. First energy level. What is next? 2s. So what is n plus L value here? 1s. L value is 0 for s subshell. 1 plus 0, 1. Here 2s, 2 plus 0, 2. So there is an increase in n plus L value. There is an increase in n plus L value. So there is an increase in energy. So this 2s. Next, what about 2p? This is the different point for single electron system and multi-electron system. For single electron system, 2s and 2p have same energy. But here it is less. 2s less than 2p. Why 2s less than 2p?
N plus L value is greater.
Yes, n plus L values are like this. N plus L values are like this. Here 1, here 2, here 3. P subshell has L value 1. 2 plus 1. Okay. So like this. There is then what about second energy level? You can't take 2s and 2p together as second energy level here. Second energy level is only 2s subshell. 2p subshell is third energy level or second excited state. So ground state, first excited state, next second excited state, and continues like this. So this is third energy level, but not second energy level. Remember that. That means for single electron system, orbits are energy levels. But for multi-electron system, orbitals become energy levels. Orbital concept is significant only for multi-electron system, because for single electron system, orbit and orbitals have same meaning. 2s, 2p, next 3s, 3p, followed by 4s,
3d.
then 3d. See, look at this value. 3s, 3 plus 0, 3. 2p, 3s, both have same n plus L value. But still, 3s gets more energy because its n value is more. That's what this point says. If n plus L value is same, the energy depends only on n value. Next 3p, 4. 4s also 4. Okay, 3p followed by 4s. And what about this 3d? 5. After 3s and 3p, we expect 3d to come. but not 3D. 4s came because the n plus L value for 4s is less than that of 3D. Hope you understand. And it continues 3D, then 4p, then 5s, 4D, 5p, and so on. The Euler diagram order. Okay, so this will be now third excited state is 3s. 3s is third excited state. What about degeneracy values? It's not n square now. Degeneracy you can check for different states. What is degeneracy of 1s? Degeneracy of 1s orbital is
1.
1. For 2s, 2s is a subshell. How many orbitals are there in it? Only one.
1.
A subshell has only one orbital, whether it is 2s or 20s, it's one. Then 2p,
1.
how many orbitals are there in it? 3.
3.
So the degeneracy is 3. Next in 3s,
1.
1 again. Look at this, the values are changing. These values are not same as that of the single electron system values. Okay, now is that clear, Vishwasri?
Yes, sir.
So the degeneracy is different, and also energy levels will be different for single electron and multi-electron systems. And now for writing the electronic configuration, energy order is required. Energy order of different orbitals is required. So the energy order that is obtained based on all this order, all these values, is finally Euler diagram. Is same as Euler diagram. 5, then 5, 6, 6, and continues. What will be there after 5p? 6s, 4f, 5d, 6p, 7s, 5f, 5f, 6d, 7p, no, 7p, and 8s, all this continues. Right up to here, 7 shells. The combination of all this, the energy order is given as Euler's diagram. I'll show you that. Copied. So here it is, the Euler diagram, just look at this, no need to copy. First 1s followed by 2s, then 2p, then 3s, 3p, 4s, 3d. Look at this, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p, and 8s finally. Okay, so this is all clear. Then how to write electronic configuration? That's important. How to write electronic configuration. So how do we write electronic configuration? We'll write electronic configuration by using certain rules. What are the rules of Bohr principle? Hund's rule, and Pauli's exclusion principle. Should I explain all them in detail? Let me just give you them in short. You must be aware of them. Rules to write electronic configuration. Rules to fill. What is electronic configuration? Filling of electrons in different energy levels in a particular atom is called as electronic configuration. Writing electronic configuration is nothing but filling of electrons in different orbitals available in a particular atom. Okay. So what the rules are? First one is Aufbau principle. Aufbau means building up. It's a word. It's not name of scientist. A word which means building up. So Aufbau principle. What is the main point related to Aufbau principle? According to Aufbau principle, electrons must be filled in different orbitals in the order of their energies. Okay, electrons must be filled in different orbitals in the order of their energies. That means without completion of lower energetic orbital, electrons should not enter into high energetic orbital. Without completion of lower energetic orbital, electrons should not enter into high energetic orbital. For example, a configuration is taken like this, 2s and 2p. Here 2s, 1 is taken. They are filled like this. So what do we say now about this configuration? Does it follow or violates Aufbau principle? Does it violate or follow Aufbau principle?
Follow.
Look at this 2s. Is that completed?
Violate.
2s. What is capacity of each
2 electrons.
orbital?
2.
2 electrons, right? So that comes from Pauli's exclusion principle. Actually, the limitation for number of electrons in a given orbital comes from Pauli's exclusion principle. Each orbital can take maximum of 2 electrons. So all the 2 electrons must be completed in a given lower energetic electrons before entering electron into the higher energetic orbital. So it does not follow Aufbau principle. So if the same configuration is taken, what is right according to it? It should be like this. If you write like this is correct. Okay, so that is Aufbau principle. Then Hund's rule or Hund's rule. Hund's rule. What is according to Hund's rule? All degenerate orbitals must be half filled. Hund's rule of maximum spin multiplicity. So there is also another term, spin multiplicity, to be discussed here. You can write it aside. Spin multiplicity is equal to 2 into sigma s plus 1 or 2 into s plus 1, where s is small s is sigma s is written if small s is taken. If it is capital S, it is total spin. All electrons. Okay, so what this term means, we'll see. Let us know what is Hund's rule first. According to Hund's rule, the degenerate orbitals must be filled in such a way, they must be, all the orbitals must be half filled before pairing. While filling electrons, you write it, I'll just dictate Hund's rule. Pairing of electrons in degenerate orbitals, pairing of electrons in degenerate orbitals should occur only after all of them are half filled. only after all of them are half filled. That means you have this 2p subshell. You have to fill electrons in 2p subshell, and you are given 4 electrons. For which element this case arises is from carbon onwards. Up to boron, there is no problem. See, for hydrogen, only 1s electron is present. For helium, 2 electrons will be present. They will be paired. But in case of carbon, 6 electrons are there, and you need to fill 2 electrons in 2p subshell. According to Hund's rule, if 2 electrons are present, if you fill like this in the same box, this is wrong. According to him, when electrons are filled in 2 subshells, 2 orbitals like this is correct. If 4 electrons, if 3 electrons are there, you can completely half fill them like this. All the 3 are half filled. And if one more electron is present, that means like this, P2, P3, P4. If 4 electrons are there, how do you fill? It should be filled like this, and one should be paired. Anyone can be paired. Remember that. There is nothing wrong. Even this pairing is taken here or here. If I write like this, the size is increasing. You can also pair that here. This is also correct because these are degenerate orbitals. All of them have same energy. So that 4th electron can be placed anywhere in these 3. So this is also correct. Only this is wrong. And in that also, while filling electrons in the degenerate orbitals, while first filling the electrons in degenerate orbitals, the 2 electrons present in the given orbitals which should have same spin. Look at this. What this point says is, if I write the 2 electrons like this, one with plus half spin, other with minus half spin. You know, this clockwise arrow, clockwise, I mean, this, what is this? Upward arrow indicates plus half spin, and downward arrow indicates minus half spin. Okay. If I fill like this is wrong according to Hund's rule. The 2 electrons present in 2 different degenerate orbitals should have same spin. They can be plus half or minus half. The 2 electrons can be filled like this or even like this. Both are correct. The questions will be mainly framed based on this. Remember that. This is correct. This is also correct. And you calculate spin multiplicity with these values. 2 electrons are present. Okay. With plus half spin. Both are plus half. What will be the total spin if both the electrons have plus half spins? Total spin for this will be spin multiplicity value needed. Total spin is equal to plus half plus half plus 1. You take only magnitude. Take only magnitude. Total spin is 1. 2 into 1 plus 1, 3. If you write like this, what is spin multiplicity? What is the total spin of these 2 electrons? 0. One has plus half, other has minus half. Plus half and minus half, 0. Isn't it? If it is 0, what is total spin multiplicity? 2 into 0 plus 1, 1. Okay. And if you take like this, what is total spin here? Here also 3. So this is the point here. Look at this. Hund's rule of maximum spin multiplicity. That means when you fill electrons in degenerate orbitals, the total spin should be maximum. You should fill them in such a way. Total spin or total spin multiplicity should be maximum. Then according to spin multiplicity rule or Hund's rule, the second one is incorrect where spin multiplicity is least. If it is maximum, it is correct. You understood the meaning of maximum spin multiplicity? The total spin multiplicity of electrons filled in degenerate orbitals must be maximum. That means you should fill different electrons in degenerate orbitals first by filling in different orbitals with same spin and then followed by pairing. Okay. The third rule is Pauli's exclusion principle. Exclusion principle. So what is this Pauli's exclusion principle? According to Pauli's exclusion principle, no two electrons in an atom can have same set of 4 quantum numbers. The basic statement is like this. Write the statement. No two electrons in an atom can have no two electrons in an atom can have same set of 4 quantum numbers. Same set of 4 quantum numbers. That means the internal meaning of it is the two electrons present in a given orbital should have opposite spin. The other meaning of it is two electrons present in a given orbital must have opposite spin. Look at this. If same orbital is taken, say for example 2s, I mean for 1s also you can take. For helium, there are different ways of writing configurations. Helium, it can be written like this. It can also be written like this. It can be written like this. Three different possibilities are like this. For 1s, of course, helium has only 1s subshell. For 1s subshell, what is n value for first electron, second electron, like this? For first electron, n value is 1. L value is, it is s subshell, so L value is 0. Next, m value is also 0. Similarly, for second electron also, n value is 1, L value is 0, m value is also 0. That means for a given orbital, first three quantum numbers are same. There is no difference in the first three quantum numbers. Then where is the difference? There should be a difference in the
quantum number.
fourth quantum number. So that is why I said the internal meaning of the first statement. No two electrons can have same set of 4 quantum numbers means if electrons are present in a given orbital, they must have different spin quantum numbers. That means for this S is plus half, S is also plus half. If I write like this, is this correct configuration? Is this correct
Plus half
configuration? The two electrons have same set of 4 quantum numbers.
Incorrect, sir.
That's incorrect. It should not be like that. That is according to Pauli's exclusion principle. Even if I write like this, n is equal to 1, L is equal to 0, M is equal to 0, and S is equal to minus half for both. N is equal to 1, L is equal to 0, M is equal to 0, S is equal to minus half. Okay. So this is also incorrect. This is incorrect. This is also incorrect. Same set of 4 quantum numbers. But if you write like this, they will have different spin quantum number. N equal to 1, L equal to 0, M is equal to 0, S is equal to plus half for one, S is equal to minus half for other, which is correct. That means restriction. Okay. If you place any third electron in the given orbital, if you
How can
place
we-
a third electron in a given orbital, what happens?
Didn't get you, sir.
What will be the problem? Why can't I place third electron in given orbital?
Maximum capacity is 2.
That's what I'm talking about. How do you say maximum capacity is 2?
Only 2. Okay.
The maximum capacity comes from Pauli's exclusion principle only. If you want to place any other electron, you have to place it with either plus half spin or minus half spin. Then 2 electrons will get same set of 4 quantum numbers. That
Yes,
is
sir.
not permitted according to Pauli's rule. So that's why only 2 electrons should be present in a given orbital. So that's the rule. That means if I say a particular element, like if lithium has 1s3 configuration, if lithium has 1s3 configuration, it violates which rule? 1s3, I wrote. It violates Pauli's exclusion principle because 3 electrons you filled in the same. If nitrogen has 1s7 configuration, again it violates Pauli's exclusion principle. So these are the rules by following which electronic configuration is written in different orbitals by using their maximum capacities. Each orbital must accommodate only 2 electrons, and each subshell also. S subshell can have only maximum of 2 electrons. P subshell can have a maximum of 6 electrons. P subshell as a whole. And D subshell can have maximum of 10 electrons like that. F subshell can have maximum of 14 electrons. Okay, based on these rules, that you will understand it. Then finally, electronic configuration. You know that for electronic configuration, right? How to write electronic configuration.
Yes,
Just
sir.
show you that once. Here is the file. Maybe, can you see that clearly? Or is it very low in size? Like this. First 20 elements or 30 elements you can write, but within 30 elements, you'll get some exceptions. Look at this, based on stability grounds. You will get the exceptions. Where are the exceptions? At chromium and at copper. Look at the chromium configuration. 4s1, 3d5. Because 4 is the fourth shell is later, it is written like this. While filling, 4s is first filled, then 3d. For copper also, 4s1, 3d10. Which rule is violated here? In chromium and copper configurations? Actually, 4s is first followed by 3d.
Yeah. Yes, sir.
In 4s, there is only one electron, but 3d has electrons. 4s is not
Half bow?
completed, isn't it? Yes, it's half bow because 4s is not completed, but still electrons are in 3d. So it violates half bow principle. That can be explained on the basis of stability factors. There are two different concepts to explain that stability factor. I'll also give you some more configurations with exceptions, exceptional configurations, and then we'll discuss the reason for that extra stability to even after violating of the principle. Then we'll discuss about the configuration of ions and magnetic behavior also in tomorrow's class. Okay, we'll end that. It will not take more than half an hour. We'll end that and we'll also start a new chapter, probably states of matter. States of matter in the next class itself. Okay.
Yes, sir.
Okay. Right. Let's close the class.
Thank you, sir.
Is there any problem for you to attend the class at this time daily?
Like we're missing a physics class, sir. That's it.
Yes, sir.
Okay. Sir has class in the morning session, right?
We also have, sir, for second
Yeah,
and
he
third.
takes 12th class for us.
Okay. Right.
Yeah.
Some changes needed to come.
Yes.
Otherwise, we'll change the timings. Sir may take at 6 o'clock and I can take at this time. There also
Okay,
there
sir.
won't be any problem for you, right?
No, sir.
I'll ask Sir to plan in such a way. Okay. Right.
Okay, sir.
Thank you, sir.
Okay. Thank you.
Thank you.